Ladies and gentlemen, I would like to welcome you to another exciting session of my private research project that is about the SensGuitar. I am particularly pleased to be able to talk about this work today, as my presentations on this endeavor have never been so compact as so close to the end of this research project. I've never been able to talk about so many artifacts at once as I have today, and questions will probably never be so versatile. What is my personal motivation? Why I have worked on this kind of instrument for more than 6 years? The answer is just simple and short. I experienced the challenges and hurdles by myself. Let's address the hurdles one by one. First, learning of scales, chords and songs. Where do I have to put my fingers on the fretboard when playing a C major scale? Where to put them when playing a G minor chord? Where and when do I put my fingers on the fretboard when playing a certain song? Here, rhythm and time dynamic information needs to be considered. Ninth, adaptability. In the one scenario, I would love to do a recording of my own playing. In the other scenario, I would love to integrate further musicians in my live setting. Maybe I would like to record them additionally. In another scenario, I would love to document my composing. Maybe in home sessions, I would like to do homework on scales and chords. Since each scenario demands for individual requirements, from my perspective, it was great if there was one guitar that supports numerous scenarios and adapts to my current needs. One artifact perspective on the SensGuitar refers to the physical nature of the prototype. It provides one large display that serves as fretboard. This serves as actuator by visualizing content. For instance, the SensGuitar can visualize feedback about a musician's playing. So it attempts to manipulate its environment, referring to the musician for example, in order to improve guitar playing. Further, if a touch is put onto the display serves as sensor. For instance, so the SensGuitar recognizes the musician's current playing. Alternatively, string-wise and pickup-wise audio signals can be analyzed for identifying the musician's current playing. The wood body integrates electronic boards and computing units. These refer to the cyber-physical systems, processors and communicators. For instance, these can process sensor data in order to generate feedback. Any kind of information, such as fingertips, feedback, string attacks, etc., can be communicated via wireless antenna. Traditional buttons and switches have been integrated with the sensitive instrument design and will be integrated with this prototype. This means that the buttons and switches can serve as both sensors and actuators. For instance, as the SensGuitar detects the button and switch configuration, the processing can be affected, such as the sound design. These can serve as actuators if the SensGuitar modifies the button and switch configuration autonomously. Flexible jacks can optionally be considered as input and output of audio signals. Thus, they can also serve as both sensors and actuators. For instance, these serve as sensors if external inputs such as microphones, MP3 file signals, or further instruments are inserted and recorded. On the basis of their input, the SensGuitar can process audio information. In the case the SensGuitar outputs an audio signal manipulation, the instrument attempts to manipulate its environment, referring here to the audio signal, in order to improve guitar sound appearance. Piezoelectric and magnetic pickups can be used as sensors. By them, different kinds of audio signals are input to the SensGuitar. To be more concrete, in this case we speak about 6 piezo pickup signals, 1 per string, and 2 magnetic pickup signals. The controlling display serves as controlling panel. This serves as actuator by visualizing content. For instance, the SensGuitar can visualize app information about a musician's playing, so it attempts to manipulate its environment by activating the musician in order to improve guitar playing. Further, because of its touch panel that is stuck onto the display serves as sensor. For instance, so it recognizes the musician's current controlling activities. As an interim conclusion, one can recognize that the cyber-physical system capabilities support the autonomous feedbacking and actioning by the SensGuitar. What is my research motivation? Why have I researched on this kind of instrument for more than 6 years? The answer is just simple and short from a technical perspective. First, non-digital systems. To my knowledge, electric guitars and string instruments mostly remain on an analogous level for sound, buttons, etc. Only some electric guitars are based on digital sound design. Even fewer guitars can operate on both analog and digital sound bases. Fourth, non-feedbacking systems. To my knowledge, electric guitars or stringed instruments do not provide a feedback at all. So I'm going to speak about feedbacking at electric guitars or stringed instruments first. The answer is also simple and short from a situational perspective. First, inefficient knowledge transfers. Since electric guitars or stringed instruments do not act as cyber-physical systems and are limited in their cyber-physical system capabilities, knowledge transfers are inefficient. At least, this is one key point of this presentation I am aiming for. Second, late feedback. To my knowledge, feedback of teachers, band colleagues and producers is only given on site, sharing the same physical place. Thus, the research question was the following: how can stringed musical instruments, such as guitars, be made intelligent to enhance knowledge transfer? Although shown with the example of guitars, the following accounts for any stringed instrument. Since knowledge transfers shall be improved with the aid of the SensGuitar, let's come to the foundation of knowledge transfers. In this research project, knowledge of 3 different categories has been considered. Of course, these categories and items per category do not claim for completeness, which is indicated by the dots. Each category is addressed in the following separately. In this research project, we consider 3 different forms of knowledge. Considering these 3 different kinds of knowledge forms as both origin and target, we can identify 9 different kinds of knowledge transfers. Each is clarified in the following. Please remark here, I first address basic knowledge transfers, highlighted in green. Then I address more complex knowledge transfers, highlighted in yellow. Okay, let's come to an interim conclusion. Having faced 9 kinds of knowledge transfers in typical guitar situations, one can recognize the following. Traditionally, the guitar does not support knowledge transfers well. At least, this accounts for the 9 kinds of transfers addressed and the standard electric guitar considered. Since we know the concept of knowledge transfers, let's face the traditional process design of a guitar usage. For this, at this slide, we can find a generalization of a process which shows how traditional guitars are used in typical knowledge transfer situations. As it is abstracted, it shall represent the guitar usage at different scenarios. Let's focus on the first common scenario. The musician gets guitar lessons once a week. Here, the teacher and a musician cooperate on site. Typically, the teacher presents exercises at a first collaborative session. This one. In individual practicing sessions, the musician then does homework on the exercises discussed with the teacher. Please remark, if the musician does something wrong, incorrect patterns are reinforced. From my point of view, regrettably, there is no chance for an interim feedback. Having a next session with the teacher, here, the exercise is faced in a collaborative session. Here, a feedback is generated by the teacher for improving the musician's guitar playing. Hopefully, this intervention is useful in order to correct inefficient patterns that have been reinforced during the previous week. This cycle is repeated. As many weeks as the desired output has been realized. Okay, having faced the education scenario and its knowledge transfer situations, one can recognize the following. Traditionally, the guitar is considered as a passive, tangible resource object only. In the last session, we have clarified the traditional process of guitar usage. Let's now come to a modification of a process that considers the capabilities of sense instruments. This novel process design refers to an individual research artifact. For this, at this slide, we can find a generalization of a process which shows how sense guitars are used in typical knowledge transfer situations we have clarified in the last presentation session. As the process is abstracted, it shall represent the guitar usage at the same 3 scenarios. Let's start with a general description of the new process and make it concrete by the context of the education scenario thereafter. On the top of the process, we can identify the same elements of the process we already know. Do you remember the requirement to enhance guitar usage? This is one of the most relevant requirements. Hence, the basic process remains the same. One first difference here refers to the splitting up of the practicing session into session parts. Since the first cycle is created, the traditional guitar usage is not affected at all. Here you can see the practicing session parts, and here you can see the first cycle. It's realized as long as any session shall last. Below the traditional process pictured out here, 3 further kinds of tasks are realized in parallel. First, a process step called manual feedback. Here, the guitarist is enabled by the SensGuitar and novel forms of interactions to manually feedback the current guitar playing. Please remark, the SensGuitar is considered as IT system in this case. Second, a process step called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. Please remark the SensGuitar is considered as cyber-physical system in this case. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as interaction partner with remote instances. It takes all kinds of sensors, actuators, processors and communicators into account, too. Thus, it functions as cyber-physical system, in this case, too. Let's now come to an example of the context of the education scenario. As usual, the musician gets guitar lessons once a week. Here, the teacher and the musician cooperate on site. Typically, the teacher presents exercises at a first collaborative session. In individual practicing sessions, the musician then does homework on the exercises discussed with the teacher. Please remark, if the musician does something wrong, incorrect patterns are reinforced traditionally. Because of the new sense instrument process design, the musician is supported as follows. First, a process step called manual feedback. Here, the guitarist is enabled by the SensGuitar and novel forms of interactions to manually feedback the current guitar playing. For instance, attractive fingertip positions are visualized so that the guitarist can feedback its own actions. Since the SensGuitar is considered as IT systems in this case, hopefully the practicing session part is more valuable for the musician. Second, a process step called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. For instance, the guitar corrects incorrect fingertips, late timing attacks, etc. Since the SensGuitar is considered a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as an interaction partner with remote instances. For instance, a human teacher is connected remotely and provides ad hoc feedback to the current playing. Since the SensGuitar is considered a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. Hopefully, the experiments will prove knowledge transfer optimization and positive effects on the musician's guitar playing. Having a next session with the teacher, the exercise is faced in a collaborative session. Here, a feedback is generated by the teacher for improving the musician's guitar playing. Hopefully, this intervention is from a high quality because inefficient patterns have not been reinforced during the previous week. This cycle is repeated as many weeks as the desired output has been realized. Okay, having faced the education scenario and its knowledge transfer situations, one can recognize the following. The musician is supported by the design because the SensGuitar is considered as an active IT system and as a cyber-physical system in addition. Let's now come to the demonstration of the 3 new kinds of process tasks we have identified. For this, the 3 scenarios are considered as demonstration we have clarified before. Let's focus on the manual feedback task as a first demonstration that is exemplified in the education scenario. Here you can see the conceptual demonstration of 4 novel forms of interactions. First, next notes. In the recent session, we have referred to this form of interaction as NFI1. In the figure, you can see next notes appearing as circular elements on the fretboard display. Second, fingertip type, referred to as NFI2. In the figure, you can see fingertip types that are recognizable by the colors. These highlight the circular elements of the fretboard display so that it becomes clear which finger should be taken in order to realize a tip. Third, fingertip movement, referred to as NFI3. In the figure, you can recognize the movement by arrows appearing next to the circular elements on the fretboard display. Fourth, attractive note, referred to as NFI4. In the figure, you can recognize the attractive notes as a kind of alternative appearing as circular elements on the fretboard display. With the aid of these forms of interactions, the knowledge transfer called extraction is simplified. By comparing the current fingertip position and the attractive fingertip position, the guitarist can more easily and more quickly recognize incorrect fingertips and fingertip positions. Because of the reduction of the stickiness and corresponding knowledge objects, the musician can more easily extract knowledge on a certain scale, chord or song, and feedback by himself. Thus, we can assume that the time required is reduced and the quality of music outcomes is raised for achieving the same musical performance. Experiments will show in how far these knowledge transfers indeed improve because of the SensGuitar. Let's bring this back to the SensGuitar process. Please remember, usually the musician gets guitar lessons once a week. Here the teacher and the musician cooperate on-site. Because of the new kind of process task called manual feedback and the corresponding new forms of interactions and the knowledge transfer improvements presented, the individual practicing session parts shall improve and increasing learning speed of the guitar players. At this video snippet, you can see the visualization that shows next notes. This refers to the displaying of the tip position and the corresponding string attack, highlighted in yellow. So, attractive next notes of a song or alternative notes can be displayed on the fretboard display. Since the guitarist does not have to think about what note is located at which position and is to be played by hitting which string, the extraction is simplified and knowledge transfers are improved by design. Let's now come to the demonstration of one further kind of process task we have identified. Let's focus on the automated feedback task and exemplify this with the education scenario. I do not have to mention again that usually the musician gets guitar lessons once a week. Here, the teacher and the musician cooperate on-site. In addition to regular individual practicing sessions that are improved because of the manual feedback process task we have addressed before, the following can be realized in addition. At this video snippet, you can see the feedback visualization that is generated by the SensGuitars. If a correct note position is tapped, green plus symbols indicate the tip correctness. Red minus symbols indicate the tip incorrectness. Similarly, strings are colored in yellow if they are ought to be attacked. Their green coloring indicates correct attacks and their red coloring indicates incorrect attacks. Since the guitarist does not have to think about what note is taken correctly or not after all the feedback is presented by the SensGuitar, the extraction is replaced by an internalization, and knowledge transfers are improved by design. Let's conclude the prototype demonstration of the SensGuitar we have issued today. Before addressing the experimentation, let's appraise the research outcome critically. The research question, how can stringed musical instruments, such as guitars, be made intelligent to enhance knowledge transfer, can be answered by the design of sensitive instruments. Stringed instruments are enhanced because they are set up as cyber-physical systems. Shown by the prototype, these so can function as enabling interfaces for musicians. The digital twin has been created on the basis of traditional tangible resource of guitars. Shown by the prototype, these so can support cognitive load reduction. Further, intelligence is brought to the guitar on the basis of novel forms of interactions. Shown with the prototype, these have been implemented as new forms of human-machine interfaces. The adaptation of a guitar has been enabled because of the sensing of the SensGuitar. Shown by the prototype, these so can establish a new kind of focus on individual musicians. Further, new forms of feedback and a novel feedback process have been prepared that allow sensitive instruments to optimize knowledge transfers. Since the architectural embedding of the SensGuitar has been specified, the new forms of business models are supported by the prototype of SensGuitars. We will address them in future. Taking this all together, one can say that the SensGuitar prototype supports the creation of an entire new ecosystem. Finally, the limitations shown to the left can be noted. For example, we see in the demonstration that the knowledge transfer improvement is realized on a prototype level by argumentation. It remains exciting to extend the functional proof, of course. Next steps will focus on the professionalization of the created tools, as well as the extension of the application base, the used concepts, etc. Next steps at this development iteration shall issue the prototype improvement and its experiment embedding. Then the empirical examination of knowledge transfers shall follow, which includes the observation of the SensGuitar in experiments in the field and by third test persons. For this, artifacts will be stressed by real-world conditions and an objective evaluation framework will be set up. Furthermore, it should be about communicating research results, advertising them and building up a scientific community because the SensGuitar enables numerous interesting research objects.